Welcome back to our YouTube channel. In this video on CAPS Mathematics Grade 12 and the topic trigonometry, we're going to look at geometric problems in 3 dimensions. Hi, welcome back to the Govan Mbeki Mathematics Development Centre YouTube channel. In this video for Grade 12 Mathematics, we're going to look at the topic trigonometry, and we're going to look at problems in 3 dimensions. Problems where we will apply trigonometry to solve some 3-dimension problems there. This video will consist of 4 units. The first one, I'm going to just have a brief overview of the area, sine and cosine rules for triangles, essential background knowledge that you require for this lesson. And then we're going to look at an approach to geometric problems in 3 dimensions, which will then be followed by some examples of geometric problems. And then, as usual in all my videos, there's an exercise worksheet for you to practice. Let us just briefly look at the area, sine and cosine rules for triangles. Let us first consider the solution of right-angled triangles. Here we have a right-angled triangle ABC, with angle C being the right angle. AB is the hypotenuse, BC is the opposite to angle A, and AC here, which is the adjacent to side to angle A. Right? We can see there's angle B, and the side opposite there is the lowercase b. There's angle C, and the side opposite is the lowercase c. There's angle A, and the side opposite is the lowercase. And this is the notation that we'll use, and I'm color coding it to assist us there. Now, if we are given any 2 sides in a right angle triangle, we can always work out the length of the 3rd side, making use of, that's correct, we can make use of the theorem of Pythagoras, right? So if I have A and B, I can work out C. If I have B and C, I can calculate A. So in a right angle triangle, if you have 2 sides, you can always work out the 3rd side. But what if we have a angle and a side? Then there are trigonometrical ratios that can be applied. First of all, sine of A is A over the C, or the opposite over the hypotenuse, right? Or I can take cosine of A, that is the relationship between the B, the adjacent, and the hypotenuse. Or if I take tangent of A, that is the relationship between the opposite and the adjacent. So those are the trigonometrical ratios we can use for solving right angle triangles. For example, if I know angle A and I know this lowercase c, I can work out A. If I want A with C, I have to use the sine ratio. If I have angle A and C and I want B, I can find use the cosine ratio. Or if I have angle A and this opposite side, I can find this one making use of the tangent ratio, right? The area of a triangle, in a right angle triangle, we can just use our standard formula, half base times height, where this adjacent is the base and the opposite in this case is the height there, right? So in a right angle triangle, this is what we can use for solving right angled triangles. Let's go over to triangles that are not. Let's consider the area rule for triangles here. In this case, we've got a triangle. You can see this is not a right angle triangle. So if we take angle A, if we are given angle A, then the area rule for the triangle would be half. Then we use the adjacent sides B and C. There's angle A, so that's sine A, so it's half BC sine of A. You can see A is included, and C and B is 2 adjacent side by angle A. Or if we have angle B again, there's angle B, we need these 2 adjacent sides C and A, it's half A and times C sine of B. Or if we have the 3rd angle, then it will be C, and then I use the A and the B, right? You can see this is triangle ABC. If I have A then I have to use the sides, the lowercase b and c. If I have angle B, I have to use the other two sides there, which is A and C. If I have C, then I have, see there you've got A, B, C, A, B, C, A, B, C. All three are, so it's the angle with the two adjacent sides there. Now the area rule can only be applied if I have two sides and it must be an included angle. Let's just look at that. You can see there's the two sides, there's a side and another side. The angle must be included. I can't have that angle here, so it must be an included angle. So the area rule will only apply to the side angle, side case there. Now let's look at the sine rule for any triangle. There we have the one version of the sine rule, and this formula is given in grade 12, or we can have the formula in this form here, right? So you can see there I've got the sides in the numerator and the angles in the denominator. Here I've got it the other way around. Now, normally learners want to know, or students want to know, when should we use it in this form and when it can be used in that form. Now, in this case here, if I have got the sides in the numerator, this is the version I use if a side needs to be calculated. So if they want the length of a side, preferably use this version of it, because then you've got the sides in the numerator, right? Or if you want to calculate an angle, then you use the version where the angles are in the numerator. That's just a little bit of advice there, but it doesn't matter which one of the two you use, but it's very helpful if you want to find a side. Preferably use that because it's much easier making that side the subject of the formula there. Now let's look at the case where the sine rule can be applied. The sine can be applied only in two situations here. If two sides and a non-included angle is given, so we have two sides, you can see there's two sides and the angle is not included. There's the angle, right? So it's two sides and it's a non-included angle. Or that we have one side only and two other angles. So we've got one side and two other angles there. So it's a side and two angles. Now let's look at the cosine rule for triangles. Right? We've got triangle ABC. Let's look at the first rule here. A squared and I have cos A. So if I have angle A, it will be associated with the opposite side. So angle A, if I have cos A, it will start with A squared. If I have the angle B is known, so angle B is known, then I will start with B squared. Or if I have angle C, then I will start with C squared. If we just look at this formula here, A squared equal to B squared plus C squared, that there reminds you of the theorem of Pythagoras. So this is just modifying the theorem of Pythagoras there. Because if I have if this angle C, for example, is 90, this would have been the hypotenuse. Now you can see this is less than 90, therefore it's going to be smaller. So you can see that's why we subtracting there, right? So the formula is A squared plus B squared plus C squared. Then we subtract, we have to, it will definitely be shorter. Then it will be twice the B times the C and cos of the angle that's involved there. Okay. And that's the cosine rule. So it depends on the angle that is given. If you have angle B, then you start with B squared, right? Or if you have angle C, you start with the lowercase c squared there. There are only two cases where the cosine rule can be applied. If we have two sides and an included angles, we've shown you in the previous slide. So if you have an angle that is included, there's the two sides, side, angle, side, and then we can apply there. Or if we have a case there where we have only sides, right? So if I have a side and a side and a side, I can also apply the cosine rule. In this unit, we're going to look at a general approach to the 3D problems, right? And we're going to start off looking at some 3D diagrams. And then after that, we're going to show you a general approach that can be used for solving 3D problems. Now, first of all, we're going to examine some 3D diagrams for you to see how we can have triangles in 3 dimensions, in different planes there. Let's take a very basic one here. Here we have a rectangular block, and in this rectangular block here we have cut off one of the corners, so I have a triangle ACE. Let's just show you that. So that one is removed there. Okay, now how many triangles are actually now visible? Right, triangles. So we have, let's start on the left side. So we have ABC, there's ABC, right? And then we have one right in front, CDE, new one that we can see there, CDE, and this also in a vertical plane, goes straight up. And then we have one AFE, which is in a horizontal plane, right? And then we have the one we started with, ACE, that is in a slanted plane. So actually 4 triangles there, okay? Now looking at these 4 triangles, we must be very careful. You know, the sum of the angles of a triangle is 180. But if I look at point C here in this vertex, there are 3 angles there, the yellow one, the white one, and the green one. So I cannot add these 3 angles and get a size of BCD because they're in a different plane. So be careful that you don't add angles of one triangle with another if they are in different planes there. Now it's much better to, when you have a situation like this, you see the triangles are all next to each other. It's very helpful if you sort of isolate these triangles, or in our current situation we would say we social distance them. So let's try to social distance them there. Let's start with the ABC. Let's remove it there and we just put it on the side. We take the CDE and we remove it and let's put it outside there. And we have the AFE in there, you see. So now if you have it like this, it's so much easier to work with these triangles, because if you want to apply any of the rules, you only apply it to a single triangle, right? And you know, measurements of angles here has nothing to do with the angles there. Maybe we have, you can see that this AC is linked to this triangle because there's also a AC. And this CE is linked with this CE, right? So if I have this CE's measurement, I can use it there. The same there, I've got AE and it's linked to AE. Right? And this is what we're going to do then, and especially if you have the triangles, and if you can manage to separate them, it really will help a lot. Let's look at another diagram after this. Let's consider another situation here. Okay, here we have a rectangle ABCD, which could represent a vertical wall, right? We have a point E, which is on the horizontal plane, and EDC lies in the same horizontal plane, right? So we have EB that can be joined, and we can have EA that can be joined. As you can see, there seems to be quite a number of triangles here, right? Let's just look at the measurements that's provided for us here. So we have AD equal to 10. We've got the AED equal to 30, right? There we've got the 20 degrees for BEC, and we've got the 30 degrees for AED, and then we've got the 60 degrees in the horizontal plane for DEC. And we also have another angle EDC, which is this angle here. Okay. Now, if you look at this here, and you ask you how many triangles are actually there, right? Triangles that you can name. You see, if we look at this here, there's a B and a C, and it looks like, but that, you know, because this is 3-dimensional, that there isn't actually a triangle B something C. There's no triangle like that. Same way, we can't have E with that something and D, right? Because they're in different planes. Because that DC is a line behind there. So we've got many triangles here. So let's actually identify the triangles that we see there. Let's start with the horizontal. So there is one in the horizontal plane. That's the one DEC, right? There's a DEC. Then we have a one in the vertical, the one right in front here. That is triangle EBC. And then we have another one in the vertical plane, the one there, EAD, right? Those are the actual triangles. There are actually 3 triangles. We have another one, which is AEB, right? But if I now remove that horizontal one, be much easier. Let's put it somewhere else. So there I've got the horizontal one there, and I remove this vertical one here, EBC, and let's place it there, and I remove that one, AEB. In other words, we've isolated the triangle, so it's much easier working with them when they're isolated, or as we would say in our current situation, we social distance them, right? And then we have our other triangle AEB. So there we've got 4 triangles, and it's much easier working them if you have isolated or if you separated them there. Okay, and that is the idea with these problems. If you have triangles that are overlapping or the one behind the other, or, it's not easy, then it's much better for us to isolate them, draw them out separately. It doesn't take that much longer. And we can see from this particular example here, we'll use the triangles that has measurements, given measurements in. That 30 and that 10, so we have to use this triangle. They won't give me those measurements if you can't use it. And this EDC, that 60 and the 90 will have to be used, so we definitely need this triangle. And the same here with EBC, we have measurements there and we can use them. Maybe the white one that we have here, ABE, we don't have any measurements there, right? But there is a link between them. I can see this, if I can work out that AE, I can use it maybe in this white one, right? Or if I can work out this EC, it can help me to, I can use it in this one. And if I have that EB, I can use it in there, right? So we can actually eventually maybe calculate some measurements of that white triangle as well. It depends on the question what is given. Now normally in CAPS they would not give you a problem where there are 4 triangles that you have to work with, right? At most there'll be 3 triangles to work with, right? And this is what you need to do. If triangles are overlapping or so it's difficult to see the measurements, then you rather isolate them, right? Because so easily you can make a mistake. You see there is 60 and there is 20, and then falsely you can say maybe 60 subtract 20 is, and thinking that that is 40. That angle is not 40 because that 60 is in a different plane to that 20 there, right? And we look at another example after this as well. So separating them would really assist you. It doesn't take that long to separate the triangles. They draw them, isolate them. Let's look at another situation. There we've got ABC and we've got BCD. You can see the BCD is sort of partly hidden, right? There is a triangle there. So maybe we just, if there the triangles are next to each other, let's isolate them, let's social distance them. So that ABC, instead of having it there, just draw it separately. There's ABC. That BCD, there's the BCD, just draw it separate. Because it's much easier to use them if they are separate. Otherwise, we've got angles there, you won't know which part belongs to the triangle and which part does not. So one of the recommendations is if you have triangles overlapping or the one is behind the other one, then it's best to isolate the triangles or separate the two triangles or 3 triangles there. Now let's look at a general approach to problems in 3D. First of all, in these types of problems, it's always important to read the given information. Whatever information is given needs to be used. No information will be given if it's not needed in the solution of the problem there. Next, looking at our diagrams, if you have triangles overlapping or the one triangle is maybe behind the other, then you have to redraw them. It's best to isolate them, separate them, take them out, social distance them. So then it's much easier to use. Then in each of your triangles that you have, make sure that you try to fill in as many angle measurements as possible. If there are 2 angles, just automatically work out the 3rd angle. Now, it's important, if you have 2 or 3 triangles, you always need to identify the first triangle to be used. And you have to find a triangle that has 3 measurements. Why 3 measurements? If I look at the sine rule, it has 3 measurements required. Side angle or side angle, angle. If I look at the cosine rule, exactly the same. Side angle, side, or side. You cannot apply the sine rule or the cosine rule if you only have 2. So the triangle with 3 measurements in, that's the triangle you will start with. Now once we have that triangle, you want to normally determine the length. Now the length will determine on the question that's asked or what your second triangle, the second. And this length will be the link between the first and the second triangle. Okay? And once you have identified your triangle, let's start with the first triangle. You need to see which rule right? Depends whether you are given 2 sides and an angle, or whether you're giving 3 sides, etc. Right? So once you have a triangle, you can see which rule needs to be applied. And that's what you normally do. If there's a third one, you just repeat the process there. Now let's look at an example just to illustrate the approach. We are not actually going to solve this question. We're just going to show you the approach. Here we have a situation here. We've got a vertical tower. You can see there's a lighthouse. You've got a vertical lighthouse tower. And A, B, and C are in the horizontal plane. And we've got DBE, that's theta. And we've got BAC, that's 2 theta. And BD is equal to AC. They're both M. There's also another M here. So our objective here is to determine the length of BC. See, there's BC. We want to find the length of BC. So to illustrate our approach, there are some 4 questions we're going to ask ourselves. First of all, you're going to, as we said in our approach, fill in all the possible angles, which triangle needs to be first, why, and which rule. So we're going to do each one of these stages in the next slide. Now let's look at our diagram here, taking out the lighthouse. So you can see in this case here, the triangles are clear. ABC is not hidden behind DAB or the other way around, so I don't have to redraw them. Okay, so there's my 2 angles. I can clearly see them. Everything is clear. I don't have to redraw that. So calculate all the possible angles, right? Let's look at the first triangle here. I've got a theta and a 90, so I can work out the third angle, right, from some of the angles of a triangle. And what would that be? That's correct. Angle D is 90 minus theta. Once you calculate it, just insert it in there's the angle D, just insert it in angle D's place, 90 minus theta. If it can't fit in there, just put it on the side, and you can use a little arrow there. In the other triangle, I only am given 1 angle, so I can't work out the other 2. Which is the first triangle to be used? Right? What did we say? You need to look for a triangle with 3 measurements. Which one has 3 measurements? That's correct, the ABD, because we have an angle, and we actually have more than 3. We have an angle and an angle. We even have the third angle, so that is more than enough. I cannot use the other one because I only have 2 measurements. That's not sufficient to apply a rule, so it will have to be ABD, right? Because of the 3 measurements. In this case, we actually have 4, the one that we calculated. Now, which rule to apply? I know we have a right angle triangle, so we can use our trigonometrical ratios. But I would advise here that if you have, just look at the information. I've got an angle and an angle, and I've got more than 1 angle. As soon as we have more than 1 angle, we can always apply the sine rule. So I would suggest applying the sine rule instead of applying your other trigonometrical ratios. Sine rule, and the reason because I have a side with 2 angles. Which length has to be calculated, right? If I now look at this triangle, I have M. To work out AD is not going to help me because it's not going to help me to get to the other triangle. So I work with a side that is common to both. So I'll calculate the AB. Why AB? Because AB is common. Even if you look at the naming of the two triangles, ABD, ABC. See, there's a AB there and a AB. So if I can use the one AB, it is the same as the other one AB there, right? So AB is common. Even the lettering can tell me there's an A and a B, and there's an A and a B. So AB is common. In the next slide, we're going to look at another problem just to show you the approach here. Now let's look at the following example just to illustrate the approach that we are doing. We won't actually solve the problem. There we have a building. We can see SR is the height. There's the building, and that SR is perpendicular to the horizontal. So PRQ is on the horizontal plane. So you've got 2 planes there. You've got a vertical plane and a horizontal plane. Okay, and we've got measurements. Angle P is 30. Angle P, these 2, that's theta, and that one in the horizontal plane is theta, and there's another theta in the vertical plane. Okay, and PQ is equal to 6, and PQ there is equal to 6. And we want to calculate the length of PR. And here's some questions that will help us to understand our approach. In the next slide, we're going to handle each one of them just to illustrate to you the approach, not actually solving the problem. Now let's look at our diagram first. What do we notice here? That the one diagram seems to be behind the other one, right? They're overlapping. It actually looks like there are quite a number of triangles, you know, because of the one behind the other one. The base is that now that we need to, because they overlap, let's draw them separately. So PQR, can just take it there as PQR. So it's much easier now to see. As you can see there, if I separate them, it's much clearer to see what are the information of each triangle. So I only have those two triangles. Okay. The next thing that we need to do is calculate all the possible angles. If I have two angles, I can find the third one. There I've got a 90 and a theta, so I can work out angle S, which is sum of the angles of a triangle, gives me 90 minus theta. Once you calculate the angle, the best is just insert it in your sketch. There we've got another triangle, a 30 and a theta. From sum of the angles of a triangle, it's 150 minus theta. So let's insert that in the sketch as well. Now we're ready. Which triangle needs to be used first? There are two. I don't guess them. We need three measurements, at least three measurements. So I've got three measurements here, and I've got more than, right? So which one are we going to use here? We need to use one with the side length given, and this is the one with the side length. So I need the side length. So it will be PQR. I cannot use, because I cannot apply the sine rule if I have angle, angle, angle. There's no rule that can be used if you have angle, angle, angle to solve triangles. And one of the sides need to be given. Which rule do we need to apply? You can see there I've got angles and sides, so it's a side and two angles. I even have three angles, so that is the sine rule. It's a side and two angles, right? At least two angles. Third angle is just a bonus there. Then which length needs to be calculated? It is a PR and there's a QR. Which one? That's right, we're going to use the QR. And why the QR? Because QR is common to the other one. See, there's also a QR. So but if I work out PR, it's not going to help me in this triangle. So it's QR. We can even look at the naming of the triangles, PQR, SQR. Right? So there's a QR and there's also a QR. So QR is common there. Now in this unit, we're going to look at some examples of problems in two dimensions, right? And here we'll be able to illustrate the use of our approach there. Now we'll see in these examples, whenever we have pause and try, you can pause the video and then do the problem on your own and then compare it to the solution, right? So whenever we see pause and try, before you look at the solution, just try to do the question on your own, do it, and then you compare it to the actual solution there as well. Now let's consider our first example. We have a diagram alongside. There we've got a diagram. PQ is the height. There's the height of a vertical building. So that's in a vertical plane. And we know height is also perpendicular. Okay. Then we have R and S. There's R and S. They are points in the same horizontal plane as Q. Right? And then we have some angles given. QRS is 65, angle S is 70, QRP is 72, and QS is 12. It's important to understand your diagram there. So you've got two triangles with the information. That building is just to illustrate the three-dimensional situation there. Let's see what the question is. Calculate the height PQ. So we want the height PQ, and we have this given information. In the next slide, we're going to show you actually the approach, how to calculate the height PQ. Now let's look at the solution. Here we have got our diagram with all the given information. We notice that it's not necessary to redraw the triangle. Why? Because all the measurements are clearly visible. No need to redraw that. Right? Let's calculate the angles that are possible. We can work out angle P. Angle P is 18. And once you calculate, it suggests that you insert it in the sketch. In the other triangle, we can work out angle RQS, which is 45 degrees. And then we can insert it as well. Now we're ready to start. But which triangle do we start with? Remember, we need a triangle with at least a side length. That excludes PQR. So we can only use QRS. Right, now which rule do we apply? We've got a side and an angle, so that implies the sine rule. We're going to use QRS, but which side do we need to calculate? Not SR, because SR is not going to help us. We want to get to PQ, so we need a common side. In this case, it is QR. Now, seeing that we're working with triangle QRS, let's just focus on QRS. Cover up the other triangle. So now we can just focus on that triangle. You can use a piece of paper to cover it up. Now, we're going to pause the video for you to try to apply the sine rule in that triangle and calculate QR. I'll give you 3 minutes in which to do it. Should be more than enough. And then we start again. Let's look at the solution now. We're going to use this version of the sine rule. Why? Because it's a side we want to calculate, right? So it's better to use this version. Not wrong to use the other one, but you'll make your calculations a lot easier. We want QR. So let's insert the QR there. Start with an unknown value. QR, if we look at QR now, which angle goes opposite QR? And this angle there is 70 degrees. So that's a 70-degree angle. Then the other given measurement is 12, so we need 12 there. And the angle that goes with 12 is, that's correct, 65 degrees. Right, now it's easy. Instead of dividing by 70 degrees, we do the inverse. Therefore, we multiply by 70 degrees. Okay, this is just calculator work. Let's do it carefully. And that gives us 12,44. Suggested when you calculate something, just insert it in your sketch as well. Now we're going to the other triangle, PQR, because we want to calculate PQ. Okay, so triangle PQR, we want to find PQ. Right, let's get that triangle back again and let's cover up the other one. Right, so we can just focus on triangle PQR, so we don't have any distractions of the other triangle there. Now let's pause the video again. You're going to use the sine rule again. Let's pause it and give you, in this case, by now you should know, 2 minutes. Okay, let's look at the solution. Again, we want a side length, so we use this version. PQ insert, the angle opposite PQ is 72 degrees. And the other length, we just worked out 12,44. And 12,44 is opposite that, 18. Can you see now? We needed that 18 that we worked out earlier. Instead of dividing by 72, that's correct, we multiply by sine 72. And then it's just calculator work. And there we've got the answer, 38,29. And there we solve the question. Now let's consider a second example. In this example here, the angles are not given in the exact degree, right? It's given in terms of theta and theta. We don't have a length, we have it in terms of x, right? Same idea, we just don't have numerical values for the sizes of the angles and the length of the sides. So let's see now. There we've got a figure. A, B, C are 3 points on the horizontal plane. You can see there it's on the horizontal plane, grounded there. And TA represents the height of this building, this vertical building. And we've got some measurements given. Angle D is theta, right? There's angle D. Angle C is theta, and angle ABC is also theta. And BC is X units there. And we want to prove this. You see there's no degree measurements for the angles. It's in terms of theta, no length in terms of meters, or right? So we've got it in terms of X. So that's the only difference here. And let's look at the solution in the next slide. Now let's consider the solution. There we have our diagram with all the given information in, right? If we look at this diagram, we see there's no overlapping. All the information of the one diagram is clearly visible, and the other triangle is also clearly visible, right? So let's just start filling in the angles. Which angle can we calculate? That's correct, angle DBA. That's 90 minus theta, and let's insert it in the sketch, right? Then you can also work out angle BAC, which is 180 minus 2 theta, and also let's insert it in the sketch there, right? Now we're ready to start. But which triangle do we start with? We need a triangle with a side length. That means we go to ABC. That's the The other one is not going to help us. ADB is not going to help us. So we have to start with ABC. Right? Now, which rule do we apply? If we look at ABC, we've got a side and an angle and an angle and an angle. We've got more than enough for the sine rule. So we're going to use the sine rule. So we're going to take triangle ABC. Right? But we need to know which length are we going to work out. X, is it AC or AB? Right? We're going to work out AB because AB is common, belongs to the other triangle. So we're going to work with AB. Okay? Now, it's best to just cover up the triangle so we can only focus on the triangle that we're using. Only this one. We don't need the distraction for the others there. So just cover it up. Now, let's pause the video and you try to do the solution using the sine rule. Come, 3 minutes, more than enough. Now let's look. We're going to use this version. Why? Because we want a side length, and it's better to use this version. So which is the side length? AB is start with the unknown, and the angle opposite AB we can see is theta. So there I have theta, and then the other side is x. That's a given side x, and then the angle that goes with x is our 120 minus 2 theta that we worked out. Okay, because we want AB, we need to get, instead of dividing by sine theta, we do the inverse, so we multiply by sine theta. So it's x times sine theta. But 180 minus 2 theta, sine of that, you can reduce that. And if we reduce that, we end up with sine of 2 theta, right? So we change that from using our reduction formula, sine 2 theta. But now we end up with sine 2 theta, which should remind you of, that's right, it's a double angle identity. So we replace it with a double angle, 2 sine theta, cos theta identity. Okay. Now we can simplify. There's a sine theta and a sine theta, so let's cancel out the sine thetas, and that leaves out with x over 2 cos theta. So there we calculated the length of AB. When you calculate something, it's advisable to just insert it in your diagram. So there you have it. So we did the first part of the question, right? Our first stage, we worked out AB. Now let's go to the next. Let's continue with this question here. There we have our diagram with all the information. And remember, our objective is to prove that AD is equal to that expression, right? So let's see what we have there. That was what we calculated from the previous step. We found AB, and AB is x over 2 cos theta. So just we need to know that. Then we're going to now go to the other triangle, which is triangle ABD. Okay. Now if I look at ABD, now let's just maybe remove the other, and the objective is to find AD, and we can apply the sine rule. So let's just remove the other triangle, so that you can just focus on this here. So we want to apply the sine rule, and you can see why. Because we've got AB is the side, and we've got angle. We actually have more than enough information to apply the sine rule, right? So let's just try to do that. Now, remember we have AB equal to x over 2 cos theta. So let's pause now, give you a chance, apply the sine rule, and find an expression for AD. This one here, maybe we can give you 4 minutes to do this. Let's try. Right. So you're going to apply the sine rule. You're going to use this version because it's a side that's missing. So I can start with the AD, and we can see AD is opposite the 90 minus theta. So we insert that. The other known measurement is AB. So I have to put, and it's best to put in AB. Don't put in the expression x over 2 cos theta. Right. And which angle is opposite AB? AB is opposite theta. So I have theta there. Right. Now, what do we know about sine 90 minus theta? That's correct. That's cosine of theta. And I can multiply then it's AB cosine of theta, right? Now we can bring in the AB, right? The AB that we worked out, we can replace AB with that expression there. So let's go and replace it. So I have x over 2 cos theta, and then I have this. We can simplify by cancelling out the cosines, right? And now if you write it down neatly, we end up with x over 2 sine theta, which is exactly what we were required to prove. X over 2 sine theta. And there we've proved that expression. Let's do another question after this. Let's look at another situation here. Okay. In the figure alongside, we've got AC, there's AC, and BD, they are the heights of the side walls of two adjacent. There are two homes. This one is a double story, and that's also with a little loft up there, right? But this one is 2 floors, 3 floors, and this one has got two floors there. We want the heights of the side walls, so it's the walls on the side, this side and that side. Okay, and A, B, P lie in the same horizontal plane. A, P, and B, they are points that lie in the same horizontal plane. So there's my horizontal plane there. Okay. Then we have some measurements given. BD is 6. So BD is 6 meters, which is twice AC. So what would AC be? That's correct. AC is 3 meters. APC is 15. Angle APC is 15. DPB is 40 and APB in the horizontal plane is 80. Make sure you understand your diagram. It's important you understand. Make sure all the measurements, you know exactly where they located, right? Let's see what question is asked here. We want the length of AB, so we want that length there. Okay, now let's go to the next slide to see what's the approach to this problem here. Now let's see there. There we have our diagram. Just taken the house away. So there we've got all the diagrams. We've got all the information there, right? But if we look at that, it looks very busy, right? This overlapping, this ACB seems to be in front and this one is at the bottom. So let's isolate them, right? Let's isolate. Let's apply social distancing for these three triangles there. Let's take that one, the one at the base, and let's push it up there. Okay, separate. So just draw the triangle separately. And there we've got our 3 triangles separate, so it's much easier to interpret and use the triangles. What do we always need to do? That's correct, fill in as many missing angles as possible. In APB, there is only one, we can't find the other 2, so let's forget about that. But we can calculate angle D, because of a 40 and a 90, easy, we get 50 degrees, right? Shouldn't be using a calculator for that. Then we can calculate angle C. Also, 90 minus 15 gives me 75. So we've got all them. Those are all the possible angles. We might need them, but insert them in the diagram as well. Which triangle do we start with? There are 3. Which one will we definitely not start with? That's correct, APB, because we only have one angle. That's the last one we're going to work with, right? Now let's look at this here. I can either start with ACP, because I've got an angle and an angle and an angle and a side. I can easily start with that one. So it doesn't matter whether I start with ACP or DPB, it will be the same, but we'll work with both of them. Let's start with ACP. Let's start with the one here. And there are 2 triangles. We're going to start with ACP. Which rule can we apply in each one, right? It's the sine rule of the cos with a side, an angle, that sine rule, right? It's much easier using the sine rule. So we're going to apply the sine rule, ACP, and then we want to find AP. Why AP? Because if I have AP, I can work out that I can use it there. This AP and that AP is the same. So I will work out AP. Okay, let's get rid of the triangle so we can only focus on the triangle that ACP. Just cover up the others so you're not distracted there. Now you're going to pause it and you're going to work out AB using the sine rule, right? This is very easy, 2 minutes at most. Easy. So I have AP, right? And AP goes with that angle that we had there, 75 degrees, right? And then we have the 3 that goes with the 15 degrees, right? So instead of dividing by 75, we multiply by sine 75. And now calculator work, 11,21. So there I've got 11,21, right? Now we're going to the other triangle. So we have triangle BDP. Let's take that one away so we can only focus our attention on the triangle. We don't need to look at the other one. Let's just cover it up. Less distraction there. And again here we want to find PB. Right? Because if I look at that, there's PB and PB. So I will work out PB because then I can come to that triangle. Because my objective is to get AB. Then let's look at BDP. Let's pause and try again. So you got this case also 2 minutes at most. So we apply the sine rule. So that's going to be, we want to find PB. So PB, there's PB that goes with 50 degrees. And then we have 6 which goes with 40 degrees. Let's multiply both sides by sine 50 degrees. So I get 6 sine 50. Let's go to the calculator and I got 7,15, right? So there we calculated BP, right? So we got BP's measurement, and we can insert the BP's measurement even in our diagrams. Like same way we can insert AP's measurement in our diagram. So there's that. Right? Now let's go to the next slide, because our objective is to find AB. We haven't worked out. So there's our triangle. This is the triangle we're going to work with. That AP was calculated. PB was calculated. So we're going to work with this triangle ABP, right? And we want the question wanted to find the length of AB. So which rule do we apply? So what do you notice there? Side, angle, side. And what is side, angle, side? That's correct, the cosine rule. Let's use the cosine rule now for the first time. So let's pause this and you're going to apply the cosine rule. 3 minutes at most. Okay, now let's look at the solution. Okay, so there we've got our cosine rule. AB squared will be AP squared plus BP squared minus 2 times the AP times the BP, and AB is opposite angle P, so I need cos of P. Remember they need to match. The angle P will match with the side opposite angle P. Let's do the substitution, and there we substitute those measurements as given there. AP is 11,2, BP is 7,15, and then we just, now because we want AB, we find the square root. You don't have to work it out. So it's also you can calculate that, leave the answer on your calculator, find square root, and then use the answer, right? Whichever way. And there we calculate AB's length is 12,2 meters. And there we solved our problem there. Okay. Let's go to another question. Let's look at an example number 4. There we have AC and BD, which are two vertical towers. You know, you've seen these towers all around. There's a tower and there's a much taller one. There are two towers. There's a BD, right? There's our two towers, AC and BD. And A, B, and E, these are points that lie on the horizontal plane, right? So there's our tower AC and our tower BC, right? And it's mentioned here that CE and DE are cables. See, these are cables. You can see there's other cables also, but we're looking at these two cables. And it anchors here at point E. We are given some measurements. ED is K. AEC is X. There's angle AEC is X. Angle DEB is Y. Angle EAB, this one on the horizontal plane, is W. And ABZ, the other one on the horizontal plane, is Z. Okay. And our question is to prove AC. And AC needs to be equal to this expression. Don't be intimidated by that. Just we want to find AC. So let's go to the, so it's important that you understand your diagram here, right? Make an answer, and you can see already there's one triangle and the one behind the other one, and it's very difficult to see which angle belongs where. So we're going to isolate those triangles before we start. So let's go to our, there we have our diagram, right? So the first thing is, you know, they're overlapping and it's very difficult to see which angle goes where. Very confusing. So let's isolate them, right? Let's take that one away, the one on the horizontal plane, and let's just push it up there, redraw it somewhere else, right? Then the others we don't have to, because now you can see they're clear, right? Or you can draw them separately, but in my case, it was easier for me just to push it up there. And just bear in mind, this is our objective, AC. We want AC. So let's see now. We fill in some angles, possible angles. Let's see what are the possible angles. That's correct. Angle D can easily be worked out. 90 minus Y. Angle C can be calculated. 90 minus X. And AEB can be calculated. 180 minus W plus Z. Right? So those angles can easily, this angle here fits in there, and that angle C goes there, and angle D goes there. Which of those three triangles do we start with? We need one with a length. Which one's got a length? That's correct. DBE. So I have to start with that. Starting with the others is not going to help me. So I'm definitely going to start with DBE. Right? So let's take the other triangles away. I don't need them now. Right? So I can just focus on the triangle I'm working with. And if I look at DBE, which rule? I've got a side and an angle, which tells me it's the sine rule, right? And if we apply the sine rule in DBE, and we want to find BE, right? And let's pause here, and you calculate the length of BE using the sine rule. 3 minutes, and then you come back again. So we're going to take BE, and BE goes with this angle D that we worked out, and angle D is 90 minus Y, so it's BE over sine of D, right? Then we take the given length, which is K, and K goes with the 90, right? Sine of 90 minus Y, what would that be? That will be cos of Y. So if I transpose it, it becomes times cos of Y. Sine of 90 should be easy, so I'm just putting in sine of 90 is 1. So BE is actually K cos of Y. So now I worked out my BE. So there I've just written it as over 1. It's just K cos Y. Let's go to the other slide just to continue. Let's look at there's our given diagram that we have there, right? This is our objective. We want AC. So we started with DBE, and we calculated BE's length is K cos Y. Now BE belongs to ABE, so I can use triangle ABE, right? Then I can take away the triangles that I don't need, so I can only focus on my ABE, right? Just cover up the others. Remember, we isolate them, so we just focus on that triangle there. Now we want AE, okay? Now which rule can we apply? That's correct. We can apply the sine rule. Okay, because we've got a side and an angle and an angle. Now let's give you some time to try this on your own. And 3 minutes. Apply the sine rule to work out AE. Okay, let's resume. So pause and try, and then you start again. So let's see. We want AE. So AE over sine of Z. And the other measurement is BE, so it will be BE over sine W. Don't write down K cos Y, just keep it as BE at the moment. It's much easier, just keep it as BE. I only want AE, so instead of dividing by sine Z, we times by sine Z. Now we can replace the BE. And what is BE? K cos Y. So now I replace the BE, as you can see that I substituted with K cos Y, right? So there I've got the length of AE, which is K cos Y sine of Z over sine of W. So now I've calculated AE. Okay, there's our diagram, and that's our question, right? We want to find AC. We already worked out BE, and then we worked out AE. Now we're ready to work out AC. Okay? AE was just calculated. Angle C we found right at the beginning, that's 90 minus X. Let's get rid of the, so we can only focus on the triangle that we need, right? We need triangle ACE, right? And our objective is AC, so we want AC. Which rule can we apply? We can apply the sine rule. Let's apply the sine rule, and you're going to try it now. Let's give you 3 minutes in which to do this, and then let's look at the solution. So 3 minutes is up. Let's look at there. So I want AC, remember it's the unknown length, so I put the AC, and that goes with X. So it's AC sine of X. I've already worked out AE, keep it in AE, don't write it in that form. So I have AE, and AE goes with that angle C, which is 90 minus X. What do you know about sine of 90 minus X? That's right, this is going to become cos of x. And to transpose the sine of x, I have to, instead of dividing, I multiply by sine of x. So sine of x, there's times sine of x, sine of 90 is cos of y. Now I can bring in my AE. I don't bring it in too early, it's just going to complicate the setting out there. So AE, but before we do that, AE, sine over cos, we know is an identity tan of x. Now we can replace the AE. So AE is this part here, right? So I substitute the AE, and if I can just write it down with one numerator, then I have k cos y sine of z times tan of x over sine, and we check that's exactly what we were required to find, and that's how we solved that particular problem. Let's look at another situation here. There we've got a lighthouse, right? There's a vertical lighthouse, and the height of the lighthouse is P, right? Vertical, that's why we've got a 90 there. And then we have PC and BC and D, that's in the horizontal plane, that's the shaded area in blue. And the angle of elevation of A from C is theta, so that angle is theta. BCD is also theta, and CBD is 30, and BD, this length on the horizontal plane, is 8. So we understand there, and those are the questions we want to answer, right? So we'll do that in the next next two slides. Now let's consider the solution there. There's our diagram, all the given information. No need to redraw. The triangles are clearly visible. There's no overlapping, so we don't have to redraw. Fill in the missing angles it's possible. We can find angle A, which is 90 minus theta, inserted there. We can find angle D, sum of the angles of a triangle, which is 180 minus theta, and we insert it there. Which triangle do we start with? We take the one with a length, and there we've got a length of 8, so rather use this one there, right? So we're going to start with this. So I can calculate, and then we'll calculate CB, because CB is the link with the AB there. So I'm going to start with triangle DBC. So the first question here, they even ask you to do workout. Calculate angle D, and we know it's 150 minus theta, right? Determine BC in terms of theta. So I want BC in terms of theta. So I can't use that one. So I'll have to use triangle BCD, right? So we're going to take triangle BCD. And in BCD, I've got BC, that's what I want, BC. BC goes with angle D, which is sine of 150 minus theta. And we're going to use the 8, so that goes 8, and 8 goes with theta, so that's sine of theta. Because we want BC, we transpose the sine of 150 minus theta, and there we've answered our question. BC is 8 sine 150 degrees minus theta over sine theta. Now the next question is, we also want to work out BC, but now we want it using the P and the theta. That means I must use this triangle, right? Again, I can use my sine rule. So work out BC, pause it, and you try it. So let's see. So I've got BC goes now with a 90 minus theta, so it's sine 90, and the P goes with a theta, so P goes with sine of theta. But what is sine of 90 minus theta? That's correct. We should know that is cos of theta, it's a co-ratio. Then we times by cos of theta. So BC is P cos of theta over sine theta. That cos of theta is the sine of 90 minus theta. So there we calculated BC in two ways. BC from this triangle and BC from that triangle. Okay, and we're going to use it to answer the next question there. There's our given diagram. We worked out BC from the previous question, BC in terms of sine theta, and then BC there in terms of P and theta, and this is what we want to find, P. Now BC is this expression, and BC is equal to that expression. Therefore, what can we deduce? That's correct. We can deduce that 8 sine 150 minus theta over sine theta is equal to P cos theta over sine theta. Let's pause this, put them equal, and try to simplify. This one needs a bit longer. We'll give you 5 minutes. Okay, let's see what you have done now. So we equate them. We take P cos theta over sine theta. There's there. And remember, I'm just putting the P in yellow because that's our objective. We want P alone. Okay. So I put BC is equal to that expression, BC equal to that expression. So the two expressions are equal. What do we notice here? Immediately, that's correct. The sine thetas can be removed, right? So I end up with P cos theta, 8 sine 150 minus theta. But what does this remind you of? That's right, the compound angle expansion for sine. So let's expand that. So that becomes sine 150 cos theta minus cos 150 sine theta. Okay, and that cos theta, if I transpose it, it becomes cos theta on that side. See, there's times cos theta, so I divide by cos theta. But what do we know about 150? 150 is a special angle. Sine of 150 is a half. Cos of 150 is a negative root 3 over 2. Right? Sine 150 is a half. Cos of 150 is negative root 3 over 2. We can simplify. Let's bring the half outside. Half times 8 will be 4. So I get 4 cos theta. Negative times negative is a positive. Root 3 sine theta. Okay, but this is not exactly what we want, right? The 4 is okay, we have the 4 there. Now, there I've got two terms divided by cos, so I can separate the terms. Okay, so in other words, I'm going to take cos theta divided by cos theta, and I'll take sine theta divided by cos theta. There's the root 3, and that's sine theta, right? So I've just split up the fraction there. And now what is cos theta over cos theta? That's correct, it's 1. And what is sine over cos? That's correct. So there I get a 1 plus root 3, that is 10. And let's compare 4, there's the 4. 1 plus root 3, 10, and there we've proved the question there. Now let's come to the important one. This is one for you. It's an exercise worksheet for you to apply what we've done in the previous slides and what we've done in this video. Okay, so let's just go to the first question. You can see there's a question there for the diagram, so you need to see whether it's necessary to isolate there. Let's look at the next one. You can also see you need to isolate. It's too complicated here, right? And we do the next one. There it's not necessary. All the triangles are quite clear, so we don't need to redraw any of the triangles there. Let's look at this one. This one definitely there's overlapping or a triangle in front, so it's best to separate the triangles. This one is quite clear. Triangle, triangle, there's just two triangles. Thank you very much for viewing this video. We also refer you to other grade 12 CAPS mathematics topics, and please subscribe to our channel, GMMDC, Nelson Mandela University. Thank you very much.